The title of this presentation is Robotics and Statistical Mechanics, Contact Planning, Optimization, and Approximation of Ground States of Spin Systems. To begin with a presentation overview, we'll be introducing connections and perspectives between a couple of fields which initially may appear disparate, but which we'll seek to make connections with and equivalences between different terms that are used in these fields. And the fields include robotics, statistical mechanics, and optimization. And in making these connections that we're going to be discussing, we'll want to motivate the importance of contact patterns in robotics with numerical optimization. And as a third bullet point item that we're going to be using as an outline for the presentation, we want to be able to discuss additional prospects for being able to apply a geometry of contact method, which we'll sometimes abbreviate as GOC in our conversations, which is a method that we'll be looking to expand and make connections with in other models of statistical mechanics, and to further motivate how this can be connected with the primary area of interest, which is robotics. And finally, we'll introduce characteristics of other robotic fixtures within the biomedical field that can further be studied within the GOC framework. So as an introduction, we're first going to be discussing a preprint on arXiv, which appeared earlier in the year in February, which is titled Geometry of Contact Planning for Multi-Legged Robots via Spin Models Duality. And this is from several authors at the MIT and Probable AI Lab, and other collaborators within other departments at the Institute, and also at Georgia Tech. And what the authors of this study were interested in looking at in this work was determining how geometry of contact, which is looking at how different types of robots, whether it be hexapod robots or robots with different types of degrees of freedom in different types of gates that they can assume throughout the trajectory that the robot is pursuing, can look to come into contact with different obstacles in the area or the sphere of influence that it's exploring. And in the first figure of their paper, they give one example of such a multi-legged robot, which is given by what they call a geometric and robophysical model, in which in the first item of the figure A, they demonstrate a robot which has three components, and these components, which are given by the dots, demonstrate the degree of freedom that the robot can use to wiggle or to move along its path when it's exploring different types of environments. And in the middle part of the figure, they demonstrate the dimensions and how such a robot can actually be fabricated, in which for the most part, it can have a distance of 5 centimeters for one of the components of the robot. And this component can wiggle or can move either to the left or to the right by a degree of pi over 2, or even degrees smaller than pi over 2 when it's traversing its environment. But also in figure B, they give a geometric model, what they call of the 12-legged centipede, which is also related to hexapod locomotion and other types of movement that small robots can assume, in which this hexapod is consisting of 6 types of components, which can move in a similar way to the multi-legged robot that's given in figure A, in which it can move or pivot along the first frontmost component of the hexapod robot, which can then induce motion and locomotion among the remaining 5 parts of the robot. And this another figure that they provide is giving more of a background into the hexapod locomotion that I have been alluding to and beginning to describe in the previous slide from the first figure that's given in their paper. In particular, they provide in this figure in panel B a shape space of the hexapod, which gives an example of the different types of configurations that the hexapod robot can assume when it's moving throughout an environment. One can see from the first configuration that's given in the leftmost column, in the leftmost column of the figure of panel B, you can see that the hexapod, the frontmost component is winding to the left, which then induces a motion and movement from the other remaining components of the hexapod, and that from the remaining configurations of the hexapod robot in panel B, one can observe different types of movements that the hexapod can assume, which are determined as given in panel A, the angles alpha 1 and alpha 2. Which are determined from whether the hexapod is assuming a stance whether the dots are colored either a darker color or a lighter color, which is indicating the movement of the hexapod, namely whether it's in a stance or aerial position. And besides describing very briefly the different types of robots that they're looking to describe kinematically, we can also more formally define some of the quantities and assumptions that we're imposing on this hexapod robot and on the other types of robots that they consider in this geometry of contact paper, and how it relates to optimization and statistical mechanics, which we're then going to be describing and motivating and making connections with other areas of robotics, in particular within the biomedical field. In particular, the biokinematic equation for the robots that they consider in the GOC paper is given by C, which is standing for the kinematic equation, which is given by the expression R dot, which is the derivative of the position vector of the robot, which is multiplied by a matrix A of R, which is the connection matrix, which is describing the connections between each one of the spaces within the area that the hexapod robot or any other robots that they consider is exploring. And they also impose the condition that the net force that's imposed on the robot is zero, which is given by the fact that if one takes some contact pattern, which is given by the variable capital I, if we look at one instantiation of a contact pattern, which is given by little I within big I, the summation of the parallel components and the perpendicular components of the forces that are imposed on the robot, which are each a function of the kinematic equations, the position, as well as the derivative of the position, which is given by the position vector, vanish. And one very important aspect and what's helpful to make use of comparisons or for introducing this formalism in terms of the kinematic equations and the different types of robots that these authors consider is that it can be used to make connections between experimental and theoretical predictions. In this case, from figure 7 of the GOC paper, the authors provide a contact planning for the sidewinding hexapod, where the hexapod undergoes some type of motion, which they call a sidewinding, which we had described previously was given by the fact that the hexapod robot can induce some motion to help it explore its trajectory or its environment through some fixed trajectory and contact plan by winding one component of its body, which would then introduce a trajectory along the other remaining components of the body. And in this case, what they look to do is that they look to plot as a function of alpha 1 and alpha 2, which were the two angles or the 2 degrees of freedoms that this hexapod robot has in terms of its ability to explore a different type of particular environment in two-dimensional space, where the items R1, R2, R3, R5 through R5 and R6 are given by different points of contact that the hexapod robot would assume when it's in the nearby vicinity of these points. And one can see that depending upon the configuration of the hexapod robot, it can either have components that are either almost perpendicular to the other two components of the hexapod robot, or there can also be different types of components which are arranged in another type of manner, which can indicate the geometry of contact as well as the contact plan that this hexapod robot is performing in some fixed trajectory. And they make a comparison between the experimental and the simulation methods or the theoretical predictions, in which the experimental predictions are generated by the plot which is given in red, as well as the simulation or theoretical predictions are given by the plot that's given in blue. And they demonstrate how if you run this hexapod robot, if you let it undergo some trajectory from time is equal to 0 to some later time, which is given by time big T, you can observe some type of displacement in the X and Y directions, namely each degree of freedom in the environment that the hexapod robot is exploring, which can be determined by either if it's a 6-beat sidewinding hexapod or 4-beat sidewinding hexapod. And different videos of these trajectories are provided by the authors in their archive preprint, in which they demonstrate how the frequency of motion in the overall trajectory of the path of the sidewinding hexapod differs depending on whether it's a 6-beat or a 4-beat. And comparing such results against each other helps for improved prediction of the gate paths of different robots. And this is to say that if we know the two angles alpha 1 and alpha 2 that the hexapod can assume when it's performing its side winding walk, then we can look at different gate paths in the shape space, which are provided in figure 4 of the reference, by looking at different ways to connect the points R1, R2, R3, R4 through R5. For instance, is given in panel A, if we just want to look to go from point R4 to R3, that can be achieved by fixing some angles alpha 1 and alpha 2, which would then allow the sidewinding hexapod to reach one destination to another. Or we can construct a more complicated gate path within the shape space to connect multiple points together, which is given by these points R1, R2, R3, R4, and R5. And we can look at combinatorially many ways to connect different points together in the shape space when the sidewinding hexapod is assuming some gate path. And now we're going to get more to the connection and optimization and building up this connection with statistical mechanics, which we're going to further expand on, which the authors primarily look at first from the perspective of a Potts model. But before we get to the Potts model, we need to actually define a type of optimization problem, and we'll want to make some type of connection between finding the ground state of a spin system, which is the Potts model. In particular, the optimization problem that the authors consider is that we want to optimize over the contact paths I of phi, where each one of the contact paths that the sidewinding hexapod or any other robot can take is parameterized in the angles phi, which is given by the supremum over the displacement delta x, which can also be expressed as the summation from I is equal to 1 to n, assuming that the robot takes some countable number of steps, m, which is the integral over phi sub I of the integral of the entries of the connection matrix, which are integrated with respect to the displacement of the robot. And an alternative way to formalize the optimization problem from the previous slide is given by the fact that we can take the same optimization, which is given by a maximum over phi and I of phi of delta x, which we gave in the previous slide, but we can also look to subtract the connection or the transition probabilities of the robot from the point x, given some contact pattern I, which is the difference between these two quantities as a function of either R of I or R of I plus 1, while still taking the summation over I is equal to 1 to m. And furthermore, the optimization problem from the previous slide can again be expressed in terms of an optimization with a switching term. And this is demonstrating how one can massage and present a different type of formulation for this optimization problem, which is related to the gate problem in shape space, which is in turns related to different types of optimal paths that a robot can take when exploring its environment. In particular, from the optimization problem that we gave in the previous slide, which was given by a maximum over paths, which can also be expressed in terms of contours C in the plane in the pattern or in the contact pattern I of C. This can also be expressed in terms of a maximum over C and I of C of some penalization term associated with the path that the robot takes, as well as a summation over all of the points belonging in the contour of the difference of the transition rate given this contact path or given this contact pattern I of R of C of I minus P of X of I of R of C of I plus 1. And equivalently, furthermore, or explicitly furthermore, the contact pattern for some path that the robot pursues can be mapped onto the Potts model. The Potts model is a very well-known model of statistical mechanics, which is a generalization of the Ising model. And this model comes into play in this paper and demonstrates a connection within the GOC framework between robotics, statistical mechanics, and optimization, because the optimization over the contact pattern that we took for the sidewinding hexapod and other robots from that paper can be expressed can be mapped onto and expressed as finding the ground state of a POTS model. And this is given by the fact that the type of diagram that we presented, that we reproduced from the paper in a previous slide, which is discussing the robotic contact planning, can equivalently be expressed as a POTS model. The POTS models consist of being defined as a probability measure over some finite volume, and the POTS model is related to the Ising model because the Ising model is a POTS model with two colors, but the POTS model has the same Hamiltonian as the Ising model, just that it's adapted to be defined over arbitrarily many colors. And in this case, we can see that from the points along the circle, R1, R2, R3, R4 through R5, we can define spins on a domain wall, which is given by precisely all of the spins which lie along the boundary of some finite volume that we're defining the probability measure for the POTS model over in terms of the spins which lie on the boundary, which the authors from the geometry of contact paper label as S1 of I sub 1 through S5 of I sub 5. And this is demonstrating that by knowing the contact path or the contact pattern in the gate in the shape space that some robot takes, this optimization problem can be mapped onto finding the ground state of some POTS model. And the POTS model shares connections with several other models arising in statistical mechanics. From several preprints, so I have authored individually on the archive, I've explored different types of connections between the POTS model, and this was very interesting for me to try to think about different ways that this robotics framework could be applied to different types of models for robotic contact in other types of areas such as biomedical applications and the like. In particular, one can see that there are many types of models in statistical mechanics which are closely related to the POTS model. For instance, I've looked at renormalizing crossing probabilities in the dilute POTS model, or one can also look at the random field POTS model, or even the 6-vertex model, which shares connections with the POTS models, as well as even the long-range and homogeneous 6-vertex model and spin chains. And just to be clear, to make the presentation as self-contained as possible, the definition of the Hamiltonian for the POTS model is given by a coupling constant between nearest neighbor terms, as well as the spin at the ith term, as well as a minus lambda term for a Kronecker delta that the spins S sub I j and S sub I of j plus 1, namely the two nearest neighbor terms, have the same color, because this Kronecker delta, which is multiplying this lambda term in the Hamiltonian, is only equal to 1 if the spin at site j and the spin at site j plus 1 are equal of the same color. And now we're going to be getting into connections with other areas of robotics and discussing how the GOC framework, which the authors have discussed in terms of robotics, statistical mechanics, and optimization, can be leveraged, and what types of observations one would make for applying this framework and beginning to study how this framework would work in more of a biomedical spirited application of robotics. And for that, we're going to be looking at a thesis due to John Till, who wrote this at the University of Tennessee, which is titled On the Statics, Dynamics, and Stability of Continuum Robots, Model Formulation and Efficient Computational Schemes. And in this thesis, it's over 150 pages. He provides a discussion of many different types of robots, whether it be tendon-driven robots or continuum Stewart Go robots or other related type of robots, which can be used for biomedical applications for either allowing directed transport between different arteries of the body and other type of operations surrounding the heart or other arteries. And he gives several different types of examples of robots with different components, in which he gives a sample of continuum robot designs, some of which are related to the continuum Stewart robot, which we're going to be providing a sketch of in a later slide. And this is demonstrating in the first panel of this slide, a tendon-driven robot, which is given by a robot which has a single arm, which can be used to grab onto things or lash onto things in its environment, which is given by different types of platforms, small platforms, which are connected together through a couple of wires. And other types of examples of this robot with a single arm, which can be used to grab certain items when it's exploring different spaces are exhibited. And the CSG, or the Continuum Stewart robot, which he represents and discusses in his thesis, is given by the following schematic. So it's a robot which is given by an apparatus, which at the very bottom is driven by a linear actuator, and there is a bottom plate and a top plate, and one can introduce numerical PD modeling and mechanical engineering equations into this apparatus because the types of wires which are connecting the top platform to the bottom platform are given by a specific arrangement of angles which are given in the bottom of this diagram, which are given by either angles alpha 1 or alpha 2. And the rod ODEs come into form because there are several types of rods which connect the bottom platform to the top of the platform, which are geometrically constrained by the boundary conditions which are imposed at the base plate. And we can numerically integrate a 4-PDE system, namely a PDE with 4 systems of evolution, to provide approximations for the displacement of the CSG robot in 3 dimensions. And this is demonstrating how some of these approximations for the solution of these mechanical engineering PDE systems, which one can look at for different classes of boundary conditions, can be obtained in MATLAB, in which, relative to the base plate of the Continuum Stewart Go robot, there is different type of displacements that the rod undergo and different types of evolution equations that the rods which connect the bottom base plate to the top base plate are subject to. And data for the CSG can also be gathered experimentally, independently of numerical approximations for the displacement of each component, from an apparatus similar to the one depicted below, in which with an Xbox controller, someone can manipulate the top base plate and observe how the rod ODs would approximately the measurements that the rod ODs would approximately exhibit, which are connected to the linear actuator, which is under the bottom base plate. And the Continuum Stewart Go robot is also applicable within the biomedical space because this type of robot can be used in different types of applications from the robots which I'd introduced from the first figure of Till's thesis, in which they can look at the displacement of the rods of this robot from the rods which are connected from the bottom base plate to those which are connected to the top base plate, which can be subject to displacement either from fluids in the body rather than just moving the top base plate relative to the bottom base plate with the Xbox controller. And typically speaking, the tendon-driven robot, such as the one which is exhibited below with the helical tendon, can perform operations within the body in close proximity to the arteries and other areas. And this is exactly demonstrating how the geometry of contact framework can come into play, because it can help a robot be able to optimize its path within the body when it's subject to a different type of fluid flow by either looking at different types of optimization problems for other models of statistical mechanics that I presented from my archive preprints in an earlier slide, as well as being able to account for different fabrication methods for the robot and how the robot can navigate when it's moving throughout the body for performing a certain operation or a smaller operation of interest. And this is demonstrating how each one of the components of the helical tendon of this tendon-driven continuum robot can be subject to displacements depending upon the position of each one of the plates, which is each one of the little circles which is given in the construction of this tendon-driven robot relative to the previous one in this robot. And incorporating fluid flow within the body in single rod PDEs remains an area of research interest, which shares connections within the GOC framework. This schematic of the concentric tube robot sketch demonstrates how different types of robots can exhibit more complicated equations or dynamics of motion, which can be dependent upon incorporating single rod PDEs together, which were provided first for the Continuum Stewart Go robot, along with concentric tube PDEs, which can be used to demonstrate whether or the distance of different boundaries within each one of the rods, as well as torsional dynamics, which can relate to ways in which the tendon-driven robot can encounter torsion when it's trying to twist its arm when navigating a certain environment. And the connection of the previous optimization framework is perhaps most clearly shown from a previous paper on the loop-OM model, which comes up from statistical mechanics due to Dumino-Capon, Peled, Satoji, and Spinka, in which their work on the loop-OM model establishes a direct mapping between the loop-OM model and the POTS model, which can help us apply the GOC framework to a larger variety of spin systems, and hence realize a larger variety of optimization problems, which can help us analyze different types of paths that robots can assume, rather than the sidewinded hexapod robot in the contact patterns that it assumes. In the loop-OM probability measures given by a probability measure supported over the hexagonal lattice, which is given by x to the number of edges in the configuration and n to the number of loops, which is normalized by a partition function so that we have a probability measure. And we're sampling some configuration omega, which lies within the loop configuration supported over the hexagonal lattice with boundary condition C. And we can see that it's important to determine which type of parameter regimes we want to look at for this probability measure, because the values of different parameters that we take in the probability measure can inform the different types of contact patterns that our robot can take. In particular, we can see that when we take certain values of the parameters for values of n and x, we can see that typically the loops that we obtain in our configuration over the hexagonal lattice are very small, whereas in panel B, Dumino-Capon and co-authors demonstrate that the types of length of the loops that we have are just one, in which most of the loops are just concentrated amongst each one of the hexagons in the lattice and don't have a very high probability of extending beyond a single cell or a single face of the hexagonal lattice. And furthermore, depending upon the size of the loop relative to the finite volume, one can group together connected components of the loop and the hexagonal lattice together, depending upon the size of the loop in each cluster. And this is another figure from the paper on the loop-OM model, figure 5, which demonstrates different ways to group together loops, which are indicated by 0 clusters, 1 clusters, or 2 clusters, in which these clusters are either respectively denoted in green, red, or blue. And several other equivalent formulations of the POTS model are also found in the sharp phase transition phenomena for the Ashkin-Teller and other closely related models, in which, from a paper published in the Annals, due to Dumino-Capon, Raufi, and Tassion, we can see even another connection between the POTS model, which plays a central role in the GOC framework for formulating an optimization problem for finding the ground state, because it can be connected to even more models of statistical mechanics, which can help us characterize a broader optimization landscape and hence make more connections with the types of patterns, with the types of contact patterns and gate patterns in shape space that different types of robots can assume. And for numerical approximation of contacts, plans, paths, and gate patterns that a robot assumes, there are many potential avenues for being able to solve the PDE systems that we had indicated for either torsional components or the rod PDEs, or either the concentric rod PDEs from different types of numerical methods, which I've also considered in previous work. For one, we can look at solving different types of PDEs with the quantum singular value transformation, or even being able to test the performance of these numerical methods to classical PDE solvers with resources over the cloud in an AWS CC2 instance. And because this project, because of this project or because of the fact that this paper in the geometry of contact paper has connections with PDE models in biological physics, there can even be some potential interest in being able to look at the performance of PDE solvers in solving different types of PDE systems for either rod equations like the rods which arise in the continuums to Go robot and other closely related robots. And finally, these potential applications for being able to apply quantum algorithms for speeding up numerical approximation for contact patterns and gates that different types of robots can take in shape space is inherently related to a variational quantum eigensolver, which is a class of a variational quantum algorithm, which can be used to reformulate and recast a partial differential equation problem into an eigenvalue eigenvector problem, which is ultimately a numerical linear algebra problem. In the GitHub repository that Till provides in conjunction with his thesis work allows for us to generate some types of approximations for different types of evolution patterns and different types of shape patterns or contact patterns that different types of robots can take. And this is a point of interest, which can provide a point of comparison between classical PDE solvers and quantum PDE solvers, which continues to remain of interest. On one side, we have a classical PDE solver, which most of the time in MATLAB and Python are dependent upon fourth-order Runge-Kutta solvers, while the quantum PDE solver is determined and dependent upon a cost function and time evolution. And so far from simulations that I've ran from both sides and comparing the errors between the quantum solver and the classical solver, there doesn't appear to be much difference in that either approximation method for the PD solution performs equally well, but the quantum solver can potentially provide an exponential speed up to the classical solver in the best case. And the conclusions that we want to end the presentation with is that we introduce connections and perspectives between the fields of robotics, statistical mechanics, and optimization. And we provided further connections and built upon the geometry of contact framework provided by the MIT Improbable AI Lab and collaborators from other departments at MIT and Georgia Tech, as well as further expanding upon their approach by discussing further mappings between the POTS model to the loop-OM model, the six-vertex model, and other models of interest in statistical mechanics, all of which drew our attention to the potential of being able to apply the GOC framework for studying contact patterns in biomedical robots like those listed from Till's thesis. And thanks for your attention.